Hello everyone, we're going to do a class again remotely, and we're going to use this opportunity of having a coronavirus to actually talk about disease propagation, exponential growth, compartment modelings, and these kind of things that we use numerical models for them. They exist in many places, not just for propagation of viruses. We can do the same things in many cases when we're dealing with Earth problems or with other biology problems. Any kind of a system can be modeled as a bunch of compartments, and that's like one of the most simple models that exists out there, and they give usually a system of ordinary differential equations that can be solved together, usually nonlinear, and we will talk exactly about this kind of case today. The model we're going to be covering is called the SEIR model, where S stands for susceptible, E stands for exposed, I stands for infected, and R, which we're not going to be dealing with because in principle it's not really an interesting part of the model itself. It's usually kind of the people that are out of the game are they resistive, or basically the people that are out of it so are resistive, or really the dead people that are out of the game. So we are going to develop a differential equation for this. So this assumes that there is a population here that are susceptible to the disease. So that's the S compartment. And we're not modeling the individuals as one by one, we're just modeling it as a big group, as a density of people. And we can say that this density is continuous. So we're considering half people. Of course, this works only when the population is sufficiently large, and you can really consider a percentage, for example, of population. So if I have a very large number of people, America, China, Canada, so 30 million people, I can consider that 50% of the population and 50.001 is a continuous number. Then the idea that this, from here, if you're susceptible, you can go to be exposed. So in that case, you will carry the disease, but you're not going to actually be contaminating. From here, you'll go to infected, and then you'll be hopefully recovered and not dead. But these are the steps that usually happen, and we just want to model these kind of things. And again, everything that I'm telling you right now here is also covered in the Jupyter notebook I sent you, including the demonstration and the simulation itself. So it's a good idea that you watch this video when you are actually having the Jupyter notebook. The next thing we're going to do is we're going to derive a differential equation for each one of these components, and I will do this in the next segment. So we're now going to continue with this idea of doing this modeling, where we have these four different compartments, and each compartment behaves separately, but they have to interact together. So the first thing we have to ask ourselves is, what happens when we look at the number of susceptible people? And how does the number of susceptible people change over time? So we can write delta S divided by delta T, which is the change in the susceptible people to the change of time. Well, the question, what happens to them? So some of them becomes, of course, exposed, and the one that becomes exposed are depending on what? Well, they're depending on the number of susceptible people. More susceptible people mean more of them will become exposed, and also depends on the number of exposed people. The more exposed people will interact with the susceptible people and will cause to more exposed. So we're doing this, it's a negative change, and this is going to be with a parameter beta times ES. The parameter beta tells us what's the rate of interaction. If it's a big interaction, then between the exposed and the susceptible, then this is going to be large, and vice versa. And then we also have the interaction with the infected and the susceptible, and that's going to be another parameter we have, which is going to be gamma, and infected and susceptible. And again, this gamma can be zero, for example, if we do complete isolation, for example, of the infected people, and this isolation is perfect and nobody affect anybody, for example, of the nurses and the doctors that are treating them, then this gamma is going to be zero. Of course, in reality, it never happens. The next thing is to look at the change in the exposed people as its number of times. So first thing, it's going to be positive with exactly these two terms, because these two terms are contributing to the exposed. So we just have to say, okay, this is going to be the same, that whatever we lose here, we gain here. then some of the exposed people are going to become sick. And this is going to be the number of people that are going to be exposed and going to become sick depends on really the rate of the disease and how long it takes to incubate. So that's nothing we can control, nothing to do with interaction. And these we're losing them, so that's going to be minus alpha E. We're losing them to the infected population. Okay. Then we look at the infected population and we say, okay, the change of these guys in time, well, that's going to be positive with this term that we lost over here is gaining over here, and then some of them are going to either actually become resistive or die, so that's going to be another parameter that does not depend on us, and that's mu times I. So basically you look at if you have more of these, more of infected people, then more of them, they will actually be either healthy or dead, and this parameter mu really replaces everything. Now, if we take the time step to be close to 0, so the delta, the change, become d here, so I can replace everything with a d here, and we get a system of differential equations that describes the behavior. It's a coupled system of the people that are going to be going from susceptible to exposed to infected to resistive. Okay, and again, we're not modeling the resistive part, but the resistive is of course everything that comes from here goes to the resistive. So this is kind of the bottom of the whole thing, but it does not contribute back to the system, so we don't need it in order to solve the system. There are parameters in the system, and we should talk about them briefly. So once again, these parameters are really the parameters that are independent of, they're not under our control, are these parameters over here. And they really depend on the rate of how much exposed people become sick and how fast sick people become healthy or die. So that's basically, these are the parameters we cannot control over. On the other hand, the parameters we can control over is exactly these parameters that relates to the interaction between patients. So the parameters beta, which appears here, and gamma, which appears here, are telling you how much interaction we have between exposed people to susceptible people. This is the social distancing part, because this is people that are going around and don't know they're sick, but they may be already infecting other people. This one really tells us how well we're isolating people in hospitals. So this seems to have more control over this. It's easier to control over this, because all it means is, like you say, okay, doctors work with gloves and with protective gear, but even that is not perfect. But this one you can control better than this, and this is where the social distancing is coming. So in the Jupyter notebooks you guys have, you would be able to play with these equations and see how the equations behave as we, for example, control this one better or control this better, and maybe get to some conclusions on the steps we're taking here, and to see if these conclusions are making sense, or the steps we're doing are making sense, or that what we're doing is not going to help us, and to see how, again, what we can take from here can help us in designing public policy.